Hello guys, welcome back to Tronic Synergy. I hope you're doing well. I'm also doing well, and yeah, welcome back. So in the previous seasons we were dealing with registers and different type of registers. Most specifically we were dealing with this IC called 74LS195, which had very many modes in which you can connect it, and that's why we preferred it rather than other ICs. So, and today we have the same IC, only that this time around we have turned around, we have connected it in different way just to make things more fun and try to understand how it works internally and how it shifts data from one flip-flop all the way to another when the data is loaded into the input of the IC. So what we're going to do today, as you can see here, we have the input. So this is the input. This LED shows you what we have in this dip switch. This dip switch. So you can, as you can see, we have only turned on the first pin, which is this first yellow LED. And once the clock is high, it has fed the data to the output. So these blue LEDs right here will be showing the output of the 74LS195, and what we are going to explain is how a single switch like this shifts the data from flip-flop to flip-flop and then turns it back, and it continues with the clock pulse. It continues like that until you turn off the this switch, until you turn it off, and it remains stable, and it remains to the original place where the input bit was. So that's what we're going to do today, and I hope you enjoy. So yeah, so this is the circuit. This is the circuit that is responsible for the connection that you're seeing on the breadboard. And what we have here, so let me just try to explain. We have a very simple circuit. We have a dip switch, we have the resistors right there, we have the LEDs showing you the input from A to D, and we have our main IC, which is the 74LS195. It has different modes. It has different modes. You can connect parallel input, parallel output, parallel input, serial output, serial input, parallel output, and serial input, serial output connection using just a single IC. So it has 16 pins, and you can check the internal schematic of the IC when you search for it. Let me just show you what we had drawn before. So this is what we had before, as you can remember, and this just explain the most of the pins that we are using in the IC. So as we said, we have 16 pins. The 16th pin is the power pin, and it's not represented here. So right here, what we have the parallel input sections from P0 to P3. Then we have the output, which is the Q0 to Q3, pin number 12 to pin number 15. We have the parallel enable. So what the function of this is, just to, when you want to connect this IC into parallel input, parallel output, you have to enable this in order for you to do that kind of configuration. So as you can see here, there is a NOT, so meaning that this control, the parallel enable control, is active low. What we mean by active low is what we mean by active low in electronics is a pin or a connection where it is said to be active when it's connected to a low voltage connection, or the low voltage supply, or the negative voltage supply. So that's what we mean by active low connection. Right here you can see this NOT. So a normal operation, if you want to connect this to parallel input, parallel output, you just connect this to ground, and that's that will work properly. On pin number 1, this is pin number 1, we have the MR, which is a master reset. Normally we don't use this, but in our previous connection we used this, where we were connecting both the input pins and the output pins together to make a single data line that will act as both the input and the output when we want to read or write to write or to read what we have in the register. So normally we don't just use this. So under normal conditions, we just connect these to VCC to disable it completely. Right here on this others, and we have pin number 2 and pin number 3, which is basically a JK flip-flop. As you can see, we have the J input, the K input, and the clock pulse. And this we are going to use it in our project right now, where we are going to connect J and K together, and the clock pulse will just connect it to the clock of the circuit. So turning back on our project, as you can see, the demarcation lines just represent what we have inside the IC. There are a lot more connections inside. I've just drawn the simple ones that we are going to use in this project to try to explain what we are doing. So in this section right here, you can see the input from A to D, where we are going to connect these points to LEDs to show us which pins we have connected, and this will help us when we want to feed data. Let's say like 1011. So meaning that A will be on, B will be off, C will be on, and D will be on, or 1001. This binary for 9. So where A is on, B is 0, C is off, then D is on. So that's what we are going to, these LEDs are going to try to explain what we are doing in the deep switch. And these outputs from the deep switch will be connected to the input of the parallel input of the IC, the parallel input of the IC. The output of the IC, we are still going to represent it using LEDs. I've not drawn the output connected to LEDs, but that's what we are going to have. And right here, since the IC has a serial input, serial output connection, inside it has a JK flip-flop, which is responsible for the serial input and serial output connection. And for the serial input, we have this JK flip-flop right here, which is we are going to connect the J and K together. We are going to connect the J and K together since J interprets 1 and K interprets 0. We are going to connect it together to interpret the full data like 1011 to know where 1 is and where 0 is and where 1 is and where 0 is. So we are just going to connect all this input to Q3, which is the final output of, which is the final flip-flop of the IC. Then the output of the JK, we are going to connect it where this Q is represented. We are going to connect it to the input of the serial. We connect to the section where we are going to connect the input, the input to the first flip-flop Q1 or the D1. We are going to connect it to that point. So meaning that once we feed data in parallel manner, what we have in our IC, we have some the connection where we have talked about the parallel enable. So once we feed data, we have enabled the parallel enable. Once the data is loaded into different flip-flops, we are going to disable this. Once we have disabled the parallel enable, we are going to turn on the shift or the load or the serial data shifting of the individual flip-flop. So what we are going to do, we are going to block the parallel enable, and now the data is going to be the data which was stored initially by the parallel manner is going to shift from flip-flop to flip-flop until it goes out. Once it reaches out, it's going to enter the J and K, which the JK flip-flop, which J and K are going to interpret either 1 or a 0, and the output is going to be fed to the first flip-flop, and the data will be shifting on and on and on. So this is just a representation to show how the data will be, or the data shifts from one flip-flop to the other inside the IC. So that's basically what we are going to do. So the circuit is right here. The circuit is right here, and now what we have a data which we are going to start with it. So the data is 1. You can see this first LED is on, so 1 0 0 0. So this is the data that we have. All the other 3 are 0, and the first one is on, so it's 1 0 0 0. And once the clock is high, because the parallel enable is on, the data that is in the input is loaded to the flip-flops, and as you can see, it resembles what we have in the input, 101000. So what we are going to do, as we have said, we are going to disable the parallel. We are going to disable the parallel by turning on this switch here, which is going to block, or is going to release or reduce the amount of voltage being supplied to the base of this transistor, which is active low, which is going to make it off immediately, turning on or immediately changing the configuration of the IC to shift data rather than to feed the data directly to the flip-flops in the parallel manner. So let's just turn it on. And once it's on, you can see the data now is shifting from flip-flop to flip-flop, and then it's coming back to the original place. So shifting, coming back to the original place. So initially what we had was 1000, and once we press the shift, but we're just going to call it shift button. Once we press the shift button, it's the data that is going to shift from flip-flop to flip-flop until it goes to the last one, then goes back to the original place. And once we turn this off, once we turn this switch off, the data or the bit is going to return back to the original place since the parallel is on, like that. So the data returns back to the original place once we turn this off. Let's try another different data. Let's try something like 1101. 1101. So we have 1, this is going to remain on, 1 1, then 0. So 1 1, then 0, then 1. As you can see, as I'm manipulating the input, at the same time the output is being changed into what I had on my input, into what I've kept on my input. So basically what we are going to do is just to turn or to disable the parallel enable in order to shift this data from flip-flop to flip-flop. So let's turn on that, and immediately you can see shifting. So you can take a look at this, and in another perspective. Let me just turn it off first. You can take a look at this in another perspective. Let me just turn it off, like that. So in this configuration, you can see it's only one LED which is off at a time. So you can check, you can try to look at that LED, or try to look at it as it's going from bit to bit. It's not really easy. It's not really easy to follow the ones, because they are just lighting blue. You cannot just follow this because it's not a different color from the rest, just blue. But you can just follow this off LED because it's much easier to differentiate with the other. So just like that, you can just follow the off LED as it's moving. But that's not the case. The case is that these bits are moving all of them at the same time. They are just shifting from flip-flop to flip-flop. We can try one more configuration. We can try let's say we try something like 0110. So first one is 0, the middle one is 0, then the last one is 0. So 0110. Let's turn that on and check. You can see the output has already changed to what you have kept in the input. And let's turn on this shift, and you can see shifting. So in this configuration, only 2 LEDs will be on at a time. 2 LEDs will be on at a time. So that's basically it. You can check how this thing, you can try and make this thing at home and try to make really fun projects with it. You can make snake lights with it, where you have different configurations. You can have moving very fast. Okay, the speed at which this moving, is being controlled by the clock, which is being controlled by this capacitor right here, which is 100 microfarad. If you want it to be a little bit faster, you can change this to a much lower value than the capacitance you're using. If you wanted to make it even slower, you can just increase this value to something higher. So let me just do one where we are going to change that capacitance into something even smaller to make it run faster, because yeah, that's the goal. So as we have said, this is 100 microfarad. You see what I've gotten here is a 5.6 microfarad. Let's check in and see how it's going to behave. We just try to adjust the camera so that you can see. Yes, so just change this. Let me just turn this off because it's going to act a little weird once I've changed that. And try to really check because these are electrolytic capacitors. They have polarity. So the strip you're seeing here is the one that you connect to the negative power supply to avoid burning this out. They can actually explode to your fingers. It has ever actually happened to me once, and it was not a really fun day for me. It was not a really fun day. So once you have connected like that, let's try to see how fast it's going to move. Yes, you can see the clock is really fast. It's really fast. You can not even try to see try to see that. Okay, and these are off. Let me just try to. We can just start with these ones to try and see. Let me turn it off first. Then let's see if it's going to manage that speed. And it's moving quite fast. You cannot even see it moving as it was moving very nicely. You cannot even see it changing. Just looking like LEDs flashing here and there, but they are actually moving. They are actually moving in the way you have configured the input. Yes, so thank you very much guys for watching. Please subscribe to Tronics Energy, and hope to see you next time. So next time, what we are going to do, we are still going to work with this IC 74LS195, and we are going to have two of them. Connect it in the configuration that I promised you last time, and I didn't really quite do it. What we said is that what we are going to connect it in a way, you can see here, we say that we are going to connect it in a way, since last time we connected here the register in a way that it has single data line acting as both input and output, being controlled by write enable and read enable control externally. So we are going to have two of these, so one register like this and another one like this, having still the same 4, which these still 4 are going to be also the inputs of the other register, which will be next over here, and the data is going to be controlled by read and write enable as I did last time, and we are going to do an additional multiplexer to choose on which register we want to either store or read data from it. So that's what we're going to do next time. So I hope you'll be around, check, and yes, so thank you very much guys for watching. Please subscribe to Tronics Energy, and I hope to see you next time.